So welcome everyone after this brief break. And we have Vyshakh with us. He will tell us about Bottomonia evolution in QGP. And he's telling something beyond the Quantum Brownian regime that we heard.
So yeah, firstly, I would like to thank organizers for arranging such a lovely workshop and allowing me to participate and also give a talk here. This is my first time in ICTS. It's a very pretty campus. So this is a work that was done with Rishi at TIFR and published in PRD last year. So prior to this, you heard about, too much about open quantum systems, but in a different setting, basically, mostly in NRQCD. And he briefly mentioned about PNRQCD. So I'll expand upon it a bit and show how we can connect it to the phenomenological results. So starting, yep. Yeah, so you have heard these statements many times throughout this workshop that heavy quarks are primarily produced at the early stages of the collision, and there's barely any thermal production at the later stage. And so because of this, we expect that they experience the entire evolution of the medium, and one can hope that whatever final observables that we measure, that it will carry some of the information that it has experienced at the, let's say, at the beginning of the evolution. So it all started with, of course, Matsui and Satz, where they proposed sequential suppression of Quark-Gluon states as a signal of QGP. And it's been quite long time since their paper, and there have been quite a lot of experimental measurements on various observables of Quark-Gluon. From a theorist perspective, it's quite interesting to look at how a QQ bar state evolves in the medium as function of time, given that medium is such a violent scenario, and also it's quite strongly coupled, and etc. etc. So theoretically, BB bar is a bit more easier to study compared to CC bar states because B quarks are produced in slightly lesser number, and you don't have recombination, etc., which is a big factor that is creating problems in implementing open quantum systems for charm quarks that Blazo had talked about. So if you want to look at the scales of the problem, there is mainly mass of the heavy quark, the separation between QQ bar, and then the binding energy. So in PNR QCD, you assume that the QQ bar state is small so that you treat it as a color dipole. Okay, so this is the typical Lagrangian that you have for PNR QCD. Your QQ bar state can be written as like singlet in terms of singlet and octet fields. So S is the singlet field and O is the octet field, and you have this transition from singlet to octet by absorbing a gluon from the medium, and you also have transitions from octet to octet. So for the medium, the main scale is the temperature or the Debye mass, which is of the same order. And so if I put some numbers in this, so T, let's say around 400 MeV or so at the beginning of the evolution. And for the QQ bar state, let's say with alpha is 0.4, you get these numbers for 1/r and then the binding energy, and this sort of a separation is well maintained. So we can go ahead and use this. So you have heard a lot about the formulation of evolution equation in terms of the density matrix. I will not go through the steps in a detailed way. So I'll skip through some of them. If you have any questions, you just stop me. So as you know, the total entire system plus environment being the QGP, is, can be modeled through density matrix. And since we are looking only at the QQ area, you want to integrate out the environment variables. So you consider reduced density matrix, and one can write an evolution equation for the reduced density matrix. This is exact, but on the right-hand side, you have the total density matrix, which is a huge object. It has everything, medium, QQ bar. Okay, so it's quite complicated. So one of the assumptions that we make is that the medium influences the system, but the system doesn't influence the medium back. Okay? Basically, you're saying that the system is a very tiny part of the entire thing. So we expand the evolution equation up to second order in the interaction. So HI is the interaction part of the total Hamiltonian. So, and this is what you get. This is the red field equation. This is known in literature from quite a long time, but in a different setting. So if you see that you have an integral that goes from 0 being some arbitrary initial time, I could have written as t0, but 0 to t. So this entire thing depends on the evolution of the medium from 0 to t. So it is inherently non-Markovian. And this is not just an ad hoc thing. One can systematically expand this equation and obtain higher order correction to this. So yeah, this is the same Hamiltonian that I had shown earlier for PNRQ series, but this is in a slightly easier way to understand. Both are equivalent. So here S being the singlet and A being the octet states, and HI is the interaction, which takes singlet to octet and then octet to singlet and octet-octet transition. So this is still quite a lot of variables that need to be simplified. So we separate out the entire density matrix into blocks, one for the singlet and one for the octet. They'll be off diagonal elements, but that don't really matter. So you put all this in the red field equation and you get something like this for the evolution equation, and V being the operators that cause this transition from singlet to octet and whatever I said earlier. And you see that these are quite complicated and time dependent. So HS is the singlet Hamiltonian, HO is the octet Hamiltonian. So yeah. So what exactly is happening is that so I expanded the interaction up to second order in G. So you have a insertion of electric field at time S and insertion at time T. And depending on the relaxation of the field, you need to know how fast the field relaxes, so that you can sort of write what sort of a correlator goes into the equation. So what I mean to say is that there's a time scale between S and T, which is the relaxation time scale, which is inherent in the medium. And there is also a time scale Ts, which is the system time scale that governs how fast the system changes from, let's say, 1s to 2s. And these can be estimated as a 1 over binding energy and 1 over temperature. The Brownian motion that you heard in the last talk assumes that tau E is much smaller than tau S. So tau E much smaller than tau S means that these interactions are almost uncorrelated. Okay, so that's why the name Brownian regime. So what we want to see is to test whether this is accurate or not for epsilon states. So if you expand this, then you get the leading order term and the next leading order term, which is what Akamas was showing in his slides, but in NRK series. Yeah, so leading on, if you keep expansion up to next leading order or leading order, you can cast it in Lindblad equation. But if you see for Bottomonia, this tau s, which is inverse of binding energy, is about 450 MeV, and 1 over tau s. And the temperature is of the order of like 400 or so at the beginning. And this hierarchy doesn't really hold, so we have to solve a very general equation that I showed in the beginning. We have to solve this equation for epsilon 1s. But for epsilon 2s, it's okay because it's somewhat okay because it's a slightly weakly bound compared to 1s. So the hierarchy somewhat holds. Okay? Is everything fine?
Epsilon 2s, can you use the PNRQC?
I think, yeah, you can. I mean, as far as I remember, like you can tune this alpha such that like you can get the proper mass. But 2s it's fine, but 3s I guess might cause problems. So yeah, is everything fine? So it's still slightly complicated, and also we look at epsilon states, which are states with definite angular momentum. So we might as well write the evolution equation in angular momentum basis. And we assume that there is no dependence on m angular momentum, so we just average over it. So you get this sort of a very complicated equation, but it's quite easy to understand what this means. So it's very reminiscent of Langevin equation, where you have a term that is drag-like term, and also you have a term that is causing, that is coming from the kicks that you get from the medium. Here, the kicks being the transition to different angular momentum states. So since the interaction is dipole, in PNRQ series, you only have transitions that change L to L plus or minus 1. So these three operators are quite complicated. They have this time dependence and they depend on the Hamiltonian and such. So to calculate anything, we have to do it numerically. There's a way to do it numerically. It's known as stochastic unraveling, where you write a stochastic wave function and then a corresponding evolution equation, where so you have a Hamiltonian part, and then you also have a noise part. Here, the noise being a discrete noise, a Poisson process, meaning dn is either 0 or 1. So you have this evolution through H effective, and you also have transitions that take your state from psi to j psi. Okay? So computationally, one has to do an ensemble average over many realizations, and it's very intensive. But for ALO and NLO, it has been shown that. So for NO and NLO, it will be in Lindblad equation. It has been shown that this part can be more or less ignored for one state. And that means we only have this part, which is just a direct evolution, and there is no ensemble average. And for example, for a singlet state with angular momentum L, you have the evolution equation to be something of this sort. And you see that this is like quite complicated. Yeah, I forgot to mention what is gamma. So gamma is something that you get from tracing over the environment part. So if you see here, you have an environment trace. So you have each H has an electric field, and then you trace over it. That's where you get the gamma. So this is the interesting part about the open constant, that everything, all the medium information goes into this just 2-point correlator. So yeah, so we want to illustrate the dependence of the result, which is the suppression, on tau s and on the hierarchy between tau s and tau e. So since the binding energy is fixed, we can't really change tau s, but we change tau e by having this factor xi, which we vary in some range. And we have to pick a correlator for gamma, and there's no first principle calculation of gamma, a non-perturbative calculation of gamma, but it's reasonable to take a exponentially decreasing correlator. And this kappa is related to the, it is related to the momentum diffusion coefficient. So the spectral function that corresponds to this correlator is given by this. So basically what happens is that this object has the maximum contribution when omega is equal to the difference in energies, which is the binding energy. But this is peaked at omega equal to 0. So if your binding energy is very small, you get a larger contribution from this, but your binding energy is large, you get a slightly smaller contribution. So you can expect that as you vary this psi from smaller value to higher value, you have a decrease in suppression. So that's what we see here. This is for a constant background so I just compute this psi and then I calculate mod psi square. So I calculate the overlap of the psi with one state. So that's what we get. As we vary from small psi to larger psi, we have a variation in the survival probability, and you clearly see that LO and NLO are very different from these curves that has finite psi. And the LO results like highly overestimate the suppression. So we have, ultimately we need to compare it to experimental results. So this is with a constant background. We have also done the same exercise with hydrodynamic background. And sorry.
Am I right that your open system evolution does not have any color evolution? It's all like.
The color is there in the singlet and octet, but yeah, since I'm not including the jump part, there is no color in one. So I'm mostly looking at singlet.
Like, for example, the spectral function doesn't have any color factors. It's just completely diagonal in color.
So this spectral function, yeah, it's an ansatz. So it didn't really come from something like a.
Yeah, but the ansatz you're taking is something which is completely color diagonal.
Yes, but also there's one more point. Huh? Yeah, so there is a sum over A, and I have not written. There is also a Wilson line in between. So
in general, you'll have 2-point function of EA and EB, right? Or
so you have EA, and there is a Wilson line in between with AB index, and then there is a EB, and summed over. All these indices are summed.
Mm-hmm. Okay.
Is that fine? So yeah, so what was I saying? Yeah, so we had done the same exercise with hydrodynamic background, and this is at 5.02 TeV energies and we used the AMPT and viscous hydro temperature profiles to calculate this, and it more or less falls within the. So we have a range of psi from 1 by 1.5 to 1.5, and the data falls within the considered range. And this is plotted against n part.
The units here, it's
Sorry?
what is the units here? It's giga-electron volts, or what is
The unit.
when you say psi equal to 1.5 and so
Oh, this is just a number because, yeah, see, tau has units of 1 by
okay,
g.
okay. Psi is a coefficient of tau
Yeah,
times.
you just want to vary tau e and see. This will be around 480 or something.
Sorry?
480.
480.
Yeah, around that. I mean, it depends on the, like, which centrality I'm looking at, but let's say most
Yeah, yeah.
central, it's around 480 or something.
Yeah, because why I'm asking, because at RIC at 54 G.
I'll show you, Rick,
Okay.
this way.
So, is your Xi like a coupling, QCD coupling? Because your it
I
should
mean-
be your system scale should be D by scale. So in that sense,
Yeah, in that sense, yes. But it's a bit hard to. I wish I could say that it is QCD coupling. It's related to QCD coupling. It's a bit hard to say that because the way I have taken this correlator is a slightly ad hoc. But in HTL, one can show that you get exponentially decaying correlator with tau e being 1/md, like you said. So yeah, so this psi is like 1/g or something, at least in HTL. But in full strongly coupled, I'm not sure.
you are doing at 400 MeV.
Doing what at 400?
These calculations that you showed.
You mean this calculation?
Yeah. Of course. What?
This one?
Yeah. Oh, 300
This
MeV.
is 300. We also have 400 in the paper, but I just wanted to do a
T and is a real time, right?
sorry,
T and is a real time
where is Tn?
in that equation. That gamma T is
I'm not saying, sorry. Which slide? Which
Small
slide?
t and small s, gamma. The equation of gamma.
Gamma?
Small t and small.
Oh, this is, sorry. Yeah. This Tn is time.
and you said that in HTL for this real time correlator you get this form.
Yes, you can show that you get this one. Yeah, so this is time because you have two E fields and each of the E field has a time, like electric field. So
In your RA plot, what was the meaning of this AMPT plus viscous hydrogen? There are
so-
two different situations.
So AMPT, so after you have you have this initial condition from Glauber, they do a transport model and then they coarse grain it to hydro, I think. So it's an intermediate step between hydro and like whatever initial condition.
But there are other groups who put in some CGC like initial condition. Why didn't you take that?
I mean, see, yeah.
Oh, okay.
In here. So the average particle multiplicity, when you compare with the experimental results,
Mhm.
it's sort of at low multiplicity, the two numbers are similar, the gray box and your curve, like the colored ones. But
Yeah.
at the higher multiplicity, it sort of shifts. Why this phenomenon?
Okay. So that's because they use Monte Carlo Glauber and I have Glauber, and there is a bit of difference in parameters and also.
So are you
I mean, optical Glauber versus Monte Carlo. So
So just
geometry?
if I may,
yeah, sure.
this is not particle multiplicity. This is something called participant number. It derives directly from the Glauber modeling I was talking about. It's basically how many nucleons undergo any kind of interaction. And participant is limited by 2A, so 400. So 400 is head-on collisions where essentially every nucleon has some interaction of some low Q squared threshold. This is just counting kind of the violence of the collision, how many nucleons are. The number of participants, not multiplicity. Nevertheless, I mean, this AMPT is some Monte Carlo model and has to try to reproduce the so-called centrality or kind of impact parameter selection of the data may be good, may be imperfect. So that I think would come in a little bit
Yeah.
into the, I would say this is actually very impressive agreement by the standards of these kinds of calculations.
Yeah, so yeah, it is quite nice, but yeah, you can check out these papers too. So this is where they first started the phenomenology for Quark-Gluon with open quantum systems.
If I may, I do have a question, kind of follow up my question to the previous speaker. I mean, you've done what the other speakers did not do. You did phenomenology, and that's great.
I wouldn't say me, but they
Sorry?
started, but they start, I mean, Brambilla et al.
Yeah,
started.
so I am listening to it. I'm maybe this, this question was just asked a moment ago. I didn't quite understand the answer. So, physically, how should I understand this psi-e quantity? What do we learn? What do we learn physically about the plasma from the fact that psi-e's take some value and not some other value?
Yeah, so it's very similar to what happens for heavy quarks, that you get a kick at time t1 and you get a kick at time t2, and if they are very correlated, then you can't do something like Langevin or something. So if they are correlated kicks, then you have something like this. Sorry. So you have all these things which I told you that that you have a slightly different structure compared to what you get when you have like uncorrelated kicks. So if you have uncorrelated kicks, you can remove away all these and you get a very naive picture of what is happening in the medium. So it's basically how the field relaxes as as time passes.
Can you please explain what is correlated is here? Like charms, QQ bar are correlated, or what is
Sorry?
correlated?
Correlated in the sense that you have this function gamma t minus s. If t and s are very far away, it has a very small value. So that means in this equation, you don't really care much about the evolution that has happened, let's say, below some point in t. Is that okay? Does that make sense? So here so for your question, is a better answer. So I have an integral all the way from 0 to t. That means this entire evolution depends on the medium evolution from initial time to final time. If my correlation time is very small, okay, I can just look at around this integral around t plus minus something. I don't really care about evolution all the way from 0 because they don't have a lot of weightage from this correlator. Okay, does that make sense? Basically, it's just saying whether Markovian approximation is a good approximation or not.
I'm just asking because we are experimentally, we try to
Yeah, I
understand.
understand. But did that make sense?
So if I may follow up, so what we would like to know, I mean, physically, if you would say that to by mass, this is something physically I can understand. That's a correlation in space. There's a correlation in time. So is it is there any connection to kind of more familiar
Yes. So
physical properties?
like Sayantan was saying, is tau, one can show there in HTL that tau v is 1 over d by mass.
So it is directly related to divide.
Yes, it's directly related to
Good.
d by mass. So it has a physical significance.
Yeah, perhaps, one way to say it is that you're looking at a color electric field. If in the rest frame of the heavy quark, heavy quark is basically at rest, and you're looking at a color electric field at some time t, and the color electric field at the same point, after some delta T. And
Right, right.
you're trying to look at the correlation between that. Right?
Yes, yes, yes.
And in some sense, gamma is that. And you're asking that a color electric field at that point in this heavy quark frame, how does it kind of become uncorrelated? It's a thermal thing, right? There's a.
This is thermal, but the times are real.
Yeah, but even the real-time correlators would exponentially decay in time in a thermal state. Yeah,
Yeah, sure, sir.
So this is means just environment is correlated.
Yes, yes,
That's the-
yes, yes.
yeah, in some sense, it's a heavy quark is probing the medium, right?
Yes.
It's really this tau E is really it's a property of the environment, the
Right.
Quark-Gluon plasma,
Right, right, right.
Especially the electric field correlations of this, and you're kind of probing it with a dipole.
Yes, yes.
And you're asking, between two times, a dipole sitting, and then what does it see?
Right, right, right. Yeah. Yeah, so for 5.02, it looks good. Yeah, this is cutoff for 100, but I'll explain it later why it is. And for 2.76 also, it's reasonable. How am I doing with time?
It's fine. We have discussion.
But for Rick, where the temperature is around, let's say for the most central collisions, the temperature is around, let's say 350, something like 300, 350. One would expect that you will have a larger RAA or smaller suppression. But surprisingly, experiments see that it has the same magnitude of suppression as you see in CMS and ALICE. For me, it's very surprising. And this is what we see from our equations, that we get a larger array compared to the experimental data. So we have a couple of suspects as to why it is happening. So yeah, so within our model, just from QGP, it's not enough to explain the epsilon 1s suppression. And it is known that at RIC energies, and for JSI dynamics, cold nuclear matter effects are quite significant. So one would expect the same thing for bottom quarks, but experimentally there is no epsilon 1s data for RPA. So I can't really comment on it.
At RIC, we are doing gold. And what do you mean by cold nuclear matter effect can happen?
It's the energy. Is it a lower energy? And for charmonium, I think it is. Where's Saurav? Saurav is that? Yeah. So for charmonium, it has a significant effect at RIC compared to CMS. Let's say that's correct, right? Yeah. Yes.
So I would add another item to your list. You're using AMPT, which is a rather old and not terribly well developed model. There are much more well-calibrated dynamical models now with 3+1 dimensional hydrodynamics. And I would encourage Rishi and you to consider embedding into one of these much more calibrated models that are really reproduce a vast array of these. You don't want this disagreement to be due to the hydrodynamic model being
Right.
incorrect, because that's not the physics you're after. You want the background to be right, and then you want your formulation of the Quark-Gluon dynamics to be tested by this comparison.
Right.
So I think you could also improve the background model. You're just using it, and there are candidates we can discuss offline. That
Yeah,
I think
sure.
would be an important step to try to figure out this difference.
Yeah. Right.
And one just to follow up. So have you used the same background from LSC to here?
Same background as in same
For
temperature.
this gold?
No.
There's a different.
You use
These are, yeah,
A-
these are like independent, like,
He uses, this has AMPT.
yeah,
Not the same.
but the whatever parameters are there are tuned differently for, different. So yeah, and also we haven't included, so kappa itself has kappa over T cube has a temperature dependence, which we haven't really included it, and the temperature dependence goes like it is smaller at higher temperature, but then it rapidly increases at lower temperature. So maybe that might also influence it. So yeah, so this is the summary. I think I'm over time. But yeah, so thank you. Yes.
I have a question on your slide. I guess it's 13 or something like that.
Slide 13.
You show, yes, this one. There are two curves which are labeled LO and NLO,
Yes.
and I'm not sure I understand what this means.
Yeah, sure. Where did it go? Yes. So LO is when I set these exponentials to be 1, which is just R, and I get something.
This is moving to the interaction implementation.
Yes.
And you expand to a leading order.
Yes.
This is what you mean. And the next leading order is a T square. Is it correct?
So this is the leading order.
Yeah.
And this is the next to, combining both of this is the next to leading order.
Oh, I see.
So this is same as what Akamasu was showing, right? So you have X and then, so, but the thing is that.
In your case, the reason I'm asking is that in your case, there is a huge difference between leading order and next leading order, right? So this expansion is present. Converging very quickly. You are not using this expression.
No, he's saying for leading order, between leading order and next to leading order, there is a huge. So
you look at the plot.
Yeah.
So leading order is just taking R independent.
Yes.
And next to leading order is taking the linear dependence.
Yes.
Then if I put the quadratic dependence, what do I get?
So that's exactly that. That's why I'm not doing the expansion. So this is just to show that if you do the expansion, it's not a very good it's not a very well converging expansion. So the entire results that I have shown.
Okay. I understand. So sorry.
So that's the main thing, that I'm not doing an expansion. So expansion is what they do, Brambilla et al. In their papers. So my point is that this is not a good expansion, and the evidence being, like you pointed it out, LO and NLO. No, that's okay. Yeah, so that's the main message, that this is not a good thing to do if you expand.
Any further questions?
The expansion, but this Brambilla paper seems to explain the data just as well as you do, if not better, right? So
Yeah. So
what's the reason?
what they do is, so you have this evolution, right? And you would cut off the evolution at, let's say, wherever your crossover temperature, like 160 MeV. What they do is that they cut off the evolution at 210 MeV, saying that the model is not valid after that, but it's a ad hoc thing to do for,
Let me comment further, because there are regimes. This is presumably because you are in a regime where bound states are very important.
Yes.
Okay, so the basis for which this expansion would be valid, which is the quantum Brownian motion that you can now describe.
Yeah.
This expansion would make sense.
Right.
Okay, but you are in a regime where it is not a good representation to look at the heavy quark as in terms of coordinate basis.
Mm-hmm.
The bound state is more appropriate.
Right.
There, this expansion doesn't make any sense.
Right,
indeed.
right, right,
Okay.
right.
But it's not a general statement. It's just because you are applying this to epsilon. If you were talking about the charm quark, then
Yes.
that would be different.
This is specifically for epsilon 1.
Or epsilon. Yes.
Epsilon 1s most.
Yes, but epsilon is closer to a regime which is usually labeled as a quantum optical regime, where the bound states are really playing a dominant role.
But you're right. So one can have a mixture of Brownian evolution and the optical evolution, but those two regimes are derived from this equation in different limits, you know, or this equation in different limits.
Yes. The starting point is the same.
So, yeah. So we are not doing any approximation, right, from here. So both the limits are there, hidden inside this, and
But eventually you have to do approximation.
no, we are not doing. The only approximation we are doing is that for 1s we are not considering, you know, these jumps from. So this effective Hamiltonian. So this effective Hamiltonian still has this, you know, exponential other things. And if you write it in energy basis, you will see that it's very similar to what you see in optical regime.
The original equation that you wrote is what Akamatsu called the red field.
Yes, yeah. From there to here, from there to here, there is no approximation except for some very minor ones. But from there to here, there are no approximations.
I'm surprised, but you're right.
Yeah, but there are no approximations. You can trust me in that. Yeah. Any more questions? Yeah.
Sometimes when we say gamma is a single exponential, or when you take the spectral equivalently, taking the spectral function to be something like coming from some Lorentz kind of this thing. That's an approximation.
Yeah,
it's like
that's an approximation.
I mean, in general, you would get many time scales.
Right.
Right. You know. Yeah.
Yeah, you will. I mean, yeah, you will have, you know, other modes coming in.
Yeah.
Okay, then we close this session by thanking Vyshakh for his talk.